Good afternoon, my wonderful students. We're back, module 2.1. I hope by now, or I believe by now, you must have finished going through the first modules I was sent to you, and you have digested them and understood a lot from there. Still expecting your questions. Now we're going to look at module 2.1 quickly, molecular diffusion and transfer processes. We're going to look at introduction, mass transfer, application of one-dimensional mass transfer. One is equimolar counter diffusion, the other is diffusion through a stagnant medium, and we'll conclude. For introduction, molecular diffusion is a natural phenomenon which allows fluids in different states of temperature, concentration, momentum to move into each other on these factors balance out. So if you have a different concentration, say state A and B, there will be transfer. That is, molecular diffusion is the reason why somebody wears a perfume into the class. It's moving from a high concentration to low concentration, and you will easily start asking, who is wearing this beautiful perfume? Or who is wearing this, this perfume is unpleasant. No. Now, at some point after that diffusion, it gets to a point when equilibrium is reached or as it balances out. It might appear that that perfume is no longer there, but it's still there. It's just because there is no longer diffusion. The concentrations are balanced out. The phenomenon of dispersion by diffusion is a very important factor in transfer processes in fluids. Consider a fluid flowing in a pipe in a laminar or streamline flow. In this case, although there is randomly directed velocities of the molecules, there will be a forward movement. That is, the molecules are imposed to move in one direction, which means adjacent layers move at different velocities due to viscous drag. That's the viscosity of that liquid. So flow is also dependent on viscosity. Just like you see, if you pour water, it flows easily than when you pour something like engine oil or even red oil. When the red oil gets thicker, the viscosity becomes higher than just the one that is in fact, that's why sometimes when you have a gallon of oil, you have to go and put it to the sun. So the temperature, reduces the thickness so that the viscosity is reduced and it becomes easy for you to pour the oil out from that gallon. So random transfer between them retards the fast moving layer and accelerates the slower moving layer. There is a net transfer of momentum between the layers across the pipe. Similar transfer occurs if we had a temperature gradient or if we also have a concentration gradient. Thus, heat transfer by conduction is the same as thermal diffusion. Transfer due to concentration gradient is called mass transfer. When flow is uniform, a steady state is reached and maintained. Mass transfer. So I've said that, for instance, perfume, cooking gas, are examples of mass transfer. Now, unlike heat transfer, at least two components are required for mass transfer to take place. In mass transfer, we can have one component diffusing through a stagnant medium or equimolar counter diffusion. So mass transfer is governed by Fick's law as given by equation 1 and 2. J is a flux, that is flux of A in x direction is directly proportional to the concentration gradient. That is, change in concentration of A, change in distance. And the proportionality constant there, DAB, is mass diffusivity. Now, the second equation 2, we are considering mass flux of B, that is JBX, flux of B in the X direction, which is the same again, concentration gradient of B. And the mass diffusivity is determined experimentally for a pair of components. Of course, diffusivities increase with increasing temperature, but decrease with increasing pressure. Now, the effect of concentration on gas diffusivity is minimal at low densities. Now, we're talking about concentration. It is also concentration dependent. So we can see that for Fick's law, for mass transfer, is governed by Fick's law. Application of one-dimensional mass transfer. Remember distillation, absorption, extraction, and so on are good examples of mass transfer. A species migrating from one phase to the other. And Fick's law has shown that mass transfer operations basically dependent on diffusion processes. As you can see in that equation, we have defined the molar flux, which is dependent on the molar average velocity. Now, another important relation can be found between the molar flux and the product of concentration and velocity. So we'll get equation 3 and also equation 4, where the molar flux with respect to fixed coordinates, that is the NAX, is made up of two components. A molar flux JA, remember our JA is DAB dCA over dx. So the first component there is JA, and then the second component YA into NAX plus NBX. So we're saying a molar flux which is due to molecular diffusion and is called the concentration contribution, and the bulk motion contribution, which is the YA into NA plus NB in the X direction. That's why you have NAX plus NBX. So we know that JA and JB are molar flux relative to molar average velocity. We've said that. So we have developed another component here with respect to fixed coordinates, that is NA and NB, which is very important. Again, mass fluxes can also be defined using equation 5 and 6. So we now want to look at when it is in terms of density. We'll see equation 7. That is if the driving force for mass flux is concentration, that is mass density. We'll have our equation 8. Then if we bring up the ideal gas equation, then equations will now change to 9 and 10. That is in terms of our JAX and NAX, the mass flux and the mass flux with fixed coordinates, equation 9 and 10 respectively. We've decided not to bug you with so many of the equations. We're just mentioning the very important ones for you to note in terms of why we're discussing the equimolar counter diffusion and diffusion in stagnant media. Okay, fine, equimolar counter diffusion. Now consider two large tanks X and Y connected by a duct whose internal diameter is very small when compared to the size of the tank. Now what we're trying to do here, the two tanks contain different percentage, 70% of N2 and 30% of CO2 mixtures. Now when the valve is open, nitrogen will diffuse from where it is of high percentage to the tank where the nitrogen is not there or is of low percentage, and then CO2 will diffuse in opposite direction. That's what we mean by equimolar counter diffusion, diffusing in opposite direction. If it is assumed that the system as a whole is at the same total pressure and uniform temperature, then for every mole of N2 that diffuses, across Y, 1 mole of CO2 will also diffuse in the opposite direction. In other words, the molar flow rates of N2 and CO2 within the connecting duct are equal and opposite. This type of diffusion is known as equimolar counter diffusion. Now, in this case, taking any plane, we're now trying to analyze that equimolar counter diffusion. Taking any plane, we'll have that NA plus NB will be equal to 0, which means NA will be equal to minus NB. Remember, it is opposite direction, and we're talking about flux. Of course, this is a vector quantity. Note that in this case, the molar fluxes relative to stationary coordinates axis and the molar average velocity are identical. So we're going to look at the equation there. Well, a physical situation that closely approximates equimolar counter diffusion is the distillation of two component mixtures whose latent heats of vaporization are very close. For energy balance, 1 mole of component A diffuses to the liquid surface, condenses, and provides a latent heat to evaporate 1 mole of component B, which diffuses away with the liquid phase. Therefore, we have a case of a flux of one gaseous component being equal but opposite to that of the other gaseous component. So we now have this equation 12 and equation 13, of course, in terms of our equimolar counter diffusion equation. Now, diffusion through a stagnant medium. This is a situation where we have component A diffusing through another component B, which is stagnant. That component B is not diffusing. Good examples are air freshener. You keep the air freshener, it diffuses, and some volatile liquid. When you keep something like acetone, it diffuses through film of air, which is stagnant. The air is not diffusing. Of course, you find out that, for example, the air freshener we're talking about, if you keep the air freshener near a fan, it will disappear faster because you are now bringing in, forced convection to make the air diffuse, as well as that air freshener is also diffusing. So since component B is not diffusing, then it means that NB will be equal to 0. Therefore, we have equation, looking at our equation 14, it now boils down to equation 15. In conclusion, we've looked at mass transfer, its application in one-dimensional mass transfer, equimolar counter diffusion, diffusion through a stagnant medium. And thank you very much for listening, and I hope to see you in the next class. Thank you.